Hello. For today, I'll be discussing the output characteristics of your DC machines, particularly your DC generators, and then later on your DC motors. So I want to emphasize that the output of a generator is electrical power, and your motor, the output of the motor is your mechanical power. And since the output of the generator is your electrical power, therefore its output is taken at the terminals in the form of voltage and current, while for motors its output is mechanical power and taken at the shaft in the form of torque and RPM. Now let's talk about generators first. So as I have said in my previous video about DC generators, the performance of your generator is measured through its voltage regulation, or its ability to regulate the voltage within a certain range, because your voltage level at the terminals varies depending on its loading. As you can see in this formula, there is a difference between the voltage of the terminals when it is no load and when it is not loaded or no load, or when it is fully loaded or full load. So that's how you get the voltage regulation. That difference divided by its rated voltage, or its voltage at full load. Okay, so the thing here is that you can actually control the terminal voltage, because your terminal voltage is a function of your induced voltage at the armature. Of course, sorry, wait lang. Sorry, nawala yata ako. As I was saying, the voltage at the terminal is a function of your terminal voltage. The voltage at the terminal is a function of your armature voltage. So if you can control this armature voltage, then you can also control this terminal voltage. Of course, you have to consider the voltage drops from the armature, because well, that may differ according to the connection of your generator. For example, for separately excited generators, the voltage at the terminal here is equal to the voltage, induced voltage, less the voltage at the brushes, less your voltage drop due to copper losses. For shunt generator, you have the same formula for voltage terminal. However, for series generator, you have to consider that the voltage terminal is equal to your induced voltage at the armature, less the voltage at the brushes, less the voltage drop due to the copper loss in the armature, less the voltage drop due to the copper loss in the field, the series field. And then you have the compound generators, your long shunt and short shunt generators. Okay, yeah. So, but anyways, that's just KVL. So I hope you can perform your KVL well. And then this EA can be controlled using the flux, and well, yeah, and the RPM. Yes, the RPM. So if you want a certain RPM, or if you want to run the generator at a certain RPM, its rated RPM, then you can change EA using the magnetic field. I guess that's also one of the reasons why you want an electromagnetic generator, for you to control the magnetic field. Because if you have a permanent magnet, then it would be, I guess, if it's a permanent magnet, then you can make this magnetic flux constant, so you'll just be controlling it using the rotational speed. But anyways, that's how you control the terminal voltage, using the rotational speed and or the magnetic flux, which can be controlled if this is an electromagnet using the field current, because your magnetic flux is directly proportional to the field current. And then that's basically the output of your generator. If you want to achieve the maximum efficiency of a generator, I guess this is just for shunt generator. Yeah, this is for shunt generator. I'm not sure if I have one for series. I don't have one for series, but anyways, for shunt generators, well, efficiency is output over input. So if you want to maximize the efficiency of a machine, you want a higher input. So I guess for maximum efficiency, your first instinct would be, I want it to be 100% loaded, because that's the highest output. Highest output, yes. You want to have a high output to get a good efficiency. So your first instinct for maximum efficiency of shunt generators is to get the maximum output that you can, which is your full load. However, if you look at, well, this is for shunt generators. If you look at the output and the input formulas for maximum efficiency, for the generator, the output of the generator would be, of course, VLIL, and then its input would be the output plus the power losses at the armature plus your constant losses. So what are those constant losses for shunt generators? Well, if you want to have a good voltage regulation, then I guess it's safe to assume that you have almost constant loss in the field. That's one constant loss. Then the copper loss, the mechanical losses are assumed to be constants. So basically those are the constant losses here. Now, if the field current is really small as compared to the load current here, if the field current here is very small as compared to this current, then by KCL you can assume, well, of course, by KCL your IA is IL plus IF. But if IF is very small, then IL is almost equal to IA, or IA is almost equal to the load current. So that's one assumption here for us to arrive at the maximum efficiency. I guess the assumption here is that your IA is approximately equal to IL. So so if you compute for the efficiency, that's P out over Pn, you just substitute P out over Pn, you get this formula, and then you can simplify this further to get this formula. Now what's interesting here is that if you get the maximum efficiency, you want the denominator to be minimum. That's one. You want the denominator to be minimum. So if you get the derivative of this to get the minimum, then we can say that the maximum efficiency of a shunt generator is when your copper losses, in this case copper losses are just the armature losses, because your field, we count the field losses, which are essentially copper losses. We count those field losses as constant losses. So this is when the variable losses, or your losses at the armature, because that's the one that is variable, equal to constant losses. So when these two are equal, you get maximum efficiency. So that's it for, I don't have one for series generator, unfortunately. Terminal characteristics of generators. Well, this is for separately excited generators. This is your terminal voltage versus, or this is your load current versus terminal voltage. Of course, at no load, your terminal voltage is at EA because IL is equal to 0. So you don't have a voltage drop here. So you can say that V terminal is just EA. I guess I want to emphasize that because I want to take you to note that if it's not loaded, it doesn't really mean that the voltage at the terminal is also 0. It just means that the current at the terminal is 0, but the voltage is not equal to 0. It's actually equal to the induced voltage at the armature. Now, as the load grows, therefore your load current also grows, making the voltage drop increase. So as the voltage drop increase, therefore your terminal voltage also decrease from EA to this value. So that's what happens here. So this is for shunt generator. It's almost the same as separately excited. However, there's a further consideration that aside from the addition of this aside from this voltage drop, we also have field weakening effect. There's a weakening effect here in the field. So your voltage level actually decreases further. Then for, I guess this one is interesting. This is not the same, not the same as shunt and separately excited, because in this case, if you don't have a load, if this is not loaded, if these output terminals are not loaded, that also means that your IL is not loaded, and essentially IL is equal to IA. Therefore, IA is equal to 0 because it's not loaded, and AS is equal to 0. And since IS is equal to 0, therefore you don't have a field, and because you don't have a field, therefore you don't have an EA. So that means that for series generators, unlike shunt and separately excited, if your generator is not loaded, therefore you don't have an EA. Therefore it's also equal to 0. EA is equal to 0, V terminal is equal to 0. Okay, and then as you load the machine, your EA grows. However, your voltage terminal also grows, but the voltage drop, this difference also grows. So you have this effect at the generator terminals. So I'll pause this video in a bit to shift to motor characteristics. So I'll begin for a while. Okay, so now this is DC motors. Again, the difference of motors and generators is that your motors outputs mechanical power, therefore it's in terms of torque and RPM. So you don't have a voltage regulation for motors. What you have is speed regulation, which is this one, and this is just the same as voltage, but instead of voltage we just use RPM or speed values. So it's no load minus full load divided by full load, and this gives you an idea that the speed of the motor changes with respect to its loading. So when it's fully loaded, it actually spins spins relatively slower than your no load machine. Okay, so I'll move on to I am not sure if I have speed control. So we'll go back to the formula of the armature voltage. The difference here of the armature voltage versus generators is that for generators, the armature voltage is greater than the terminal voltage because it's a generator. The flow of power is from armature to terminal. Now for shunt, for motors, well, this is for motors in general, yeah. For motors in general, the terminal voltage is greater than the armature voltage because the flow of power is from the terminal voltage to the armature voltage. So that's why in this formula for shunt, this is for shunt motors. In this formula for shunt motors, your EA is actually equal to the terminal voltage less the voltage drop due to the copper loss on the armature. Of course, your field is on a separate. This is for shunt. Your field is not part of the KVL because that KVL is this branch here. It's this loop here. Yeah, sorry, not branch, but yeah, it's this loop here. So that's my KVL. Well, of course, I think if you consider the brushes, then you subtract another voltage there for the brushes. Okay, but anyways, so that voltage is equal to your Ponzi over 68. So to control the speed, we can isolate that speed to get this formula. Once you have that formula, now we can say that the speed of your motor is dependent on the terminal voltage and IA. It's also dependent on IA, on phi, flux, and the terminal voltage. Okay. Now usually you control the speed using the flux, not terminal voltage, because your motors are rated to operate at certain voltage, so you don't want to deviate from that voltage. You want to use that voltage. Okay, let's see. For series motors, I guess the difference of that previous formula on shunt is that for series motors, your field is in series with the armature, so you want to consider that voltage drop. And then of course, again, if you want to consider the brushes, then you subtract another voltage here for the brushes. So the EA is equal to VT minus IA times the sum of RE plus RF minus the voltage of the brushes, total voltage of the brushes. Okay, so that's also equal to Ponzi over 60A, and then you isolate N to get the formula for that. Okay, output characteristics of the motor. So unlike generators, you compare the RPM and the torque. Unlike in generators, what you compare is voltage and current. So for motors, you want to compare RPM and torque. So this is just the same as generators. As you increase the loading for motors, there is a decrease in torque. Now there is an armature reaction, but I guess for the armature reaction I'll just discuss this to not confuse you, since medyo marami na yung na-discuss ko. I'll discuss this in a separate video, probably in an example siguro, that armature reaction. But the idea is that the armature reaction, this is with no armature reaction. Now this one is with an armature reaction. So the as you increase the loading, you produce a magnetic field. Well, of course, you have the magnetic field here. You have this magnetic field here. Now, as you increase the loading of, take note, your armature is made up of coils, and these coils, as you increase the loading, receives more and more armature current, and because of that armature current, you produce another magnetic field on the coils, and that magnetic field actually aids in producing torque in the armature. That's why if you have an armature reaction, as you increase the loading, the armature reaction also, as you increase the loading, the armature reaction actually increases such that there is sufficient magnetic field to aid the machine supplementing the torque. So that's why you have a slight increase in torque. Yeah, that's why. Okay, so I guess that's it. Yeah. Now this is for series motors. What's interesting here is that the torque at full load is this one, and you have a greater torque for starting the machine. You have a greater torque for starting the machine. Yes. And then this is on the different cumulative. Yeah, this is the different reactions at full load. Okay, so I guess that's it for motors. I have motor test here, but I think this is on a different video, and yeah, I'll upload examples later. So I guess that's it muna. So take care, stay safe.